Hello, everybody. We're just going to wait for a moment to allow everyone to join, get set up. All right. Let's get started. Thank you very much for being here, everyone. Hope you've had a great Christmas and New Year, and you're ready for our schedule of 30, fingers crossed, 30 events this year. Today we have a very nice panel with 3 speakers, and the topic is, let me get this right, spatial audio technology for binaural applications, or multi-channel sound for headphones, or yeah, there are many ways of saying it. And today we are going to start with Tom Ammerman from New Audio Technology. He has been in the immersive audio game for a few decades, and he is an experienced producer, engineer, what else is there? Teacher. And he does a lot of practical workshops at sort of large conferences and things. So Tom, thank you very much for being here. I'll let you go ahead and start your presentation.
Yeah, okay. Yeah, hello everybody. Happy New Year. So it's just 10 days ago, but it feels like we are since month in the new year for me, for example. And yeah, so I'm the currently, so Shelley is right. So I did a lot. So I had some lives before. And my current life is I'm the general manager of New Audio Technology from Hamburg. And we develop software for immersive audio, and also with a great large focus to binaural audio. So let me start the screen share. So now the PowerPoint. Okay, animations are working, and there are a lot of applications. Just let me jump in here. So a lot of scenarios where immersive audio is used, and binaural is a part of immersive audio, the focus today. And but there's also immersive audio for real loudspeaker applications, like in home cinema or cinema, or as well as in industry applications. And I also I hope you see my cursor here, but I think so. There's also the industry part. I named this industry. What I mean there is theaters and planetariums and live and installations, but this domain is much larger, and I think Polly will tell us a lot about immersive audio binaural applications there. I'm really keen to see this. But now it's binaural audio, so my presentation is also about binaural audio. And it is, well, yeah, what is binaural audio? So I think that most of you know what binaural audio is. And here it is, let me distinguish this here. It's using real loudspeaker systems or virtual loudspeaker system. This is not quite correct, because binaural audio is not only virtual loudspeaker system, but a virtual representation of an audio source in our surrounding, just as regular headphones. So, and binaural audio means Hrtfs. Most of you know what Hrtfs are, head-related transfer functions. And this is the way how our brain localize audio sources in our surrounding, so in real life, just with our ears, and detect the source, detect the space, the room where we are in. And there are 3 different methods, and I'd like to point out this here just a little bit because it's important. I come back to this some slide later. There are 3 main methods to create binaural audio. And one is measuring, for example, using such a, where's my, there's the cursor with a dummy head like this Neumann KU100 here. The other method is to create it artificial, so with math, creating Hrtf. So I will not go deeper into it, how this works, but it's not a measurement method. I'm sorry. It's a mathematical approach. And the third main method is record this. So just using a dummy head. So everybody who heard these virtual haircut, it's on YouTube. This is a binaural recording that works pretty cool. By the way, here, let me give you some, or let me point out here some pros and cons of these three methods. And the pro or the cool stuff with measurements, so measure real loudspeaker systems or loudspeakers around you, is it sounds pretty realistic. So if you have a good measurement method, you really can create the experience. Damn, I missed to unmute my loudspeaker system. Then you put your headphones away and think, oh, there's no loudspeaker playing around me. So this is an effect you very often have with good measurements of your loudspeaker system. And it has interactivity. That means you can use a virtual loudspeaker system and can move sources with a panning tool, I'll show later, in a virtual room. So this is what I mean with interactivity here. The con is limited flexibility. You only can use a virtual loudspeaker system what you measured. So you can't use 8.0 if you didn't measure 8.0. And this is one of the good stuff with the artificial creation of Hrtf. So you can create whatever you want, 80.0, 8.0, 10.1, whatever you want, you're totally free. This is a pretty cool thing with artificial Hrtf processing or reproduction. It is also interactive, and but well, honestly, this is my personal opinion and my personal experience. It's not so convincing. So it sounds always a little bit, well, you can add reverbs and early and late reflections, but finally it's more or less always the same. If you listen to such measured loudspeaker systems, you hear huge differences, and not every of them you like. Just some you like, maybe some you only like for that for music, and some just for film. So it's very different. So yeah, it's special. And finally, recording, well, such a binaural recording is pretty cool, but it is what it is. No, you can't edit it. You can't use it for any interactive stuff. So this is the problem with these recordings. But, and this is what I mentioned before, why I'm pointing out this here, quality matters. Why? Well, I heard so often, hey, we do binaural here, we do binaural there, but nobody talks about what kind of binaural. And binaural is not equal binaural. So it could be very convincing, but it also could be, I think I hear something, or maybe not. So this is quality matters, means is it convincing? Is it plausible or not? And this is the reason why I like to underline this here. It is not enough to have any kind of binaural audio. You have good quality binaural audio. And here are my favorite approach, and of course the approach my company uses in audio technology. We measure real loudspeaker environments, mainly studios, so sound studios. Of course, I don't say how we measure, this is our voodoo, but we do measurements of real loudspeaker systems. Okay, I mentioned in the abstract of this presentation, creation is the main point. I also come back a little bit, some slides or some words to monitoring, it's an extra application of binaural audio. But how to bring this, how to create, and it is, well, everybody, I think the most of you know what is a DAW. It's a digital audio workstation. This is an abbreviation for the DAW. And but how to create? just using some tools in the audio workstations, you run into a lot of problems. Most audio workstations do not support immersive audio, also not surround, but especially not immersive audio. Video workstations also not support this. And if you have an audio workstation, it's on DAW, what supports immersive audio and also binaural audio, then it's very focused on Dolby Atmos, but not MPEG-H, not Sony 360, and custom formats like cinemas, domes or so, what I mentioned before. And none of these audio workstations really have an own binaural processing. These are problems if you want to go to create immersive audio. And so it's a good idea maybe to think about a plugin. And this is what we did. We created plugins. And the benefit is, the cool stuff is you can use it in your workflow. So you're not bound to an DAW. You're not bound to a special workflow of the audio workstation. You're on your own there. And you don't have any hardware because it's a plugin. You can run around with that, can do it creating immersive audio, binaural audio, on the go, or in a bedroom, or in your kitchen, wherever you are. And the price, of course, is mostly pretty good. And here, I like to, well, just give you, I mentioned this before, there is binaural audio for creation, so conic creation, so experience such an immersive audio reproduction. But there is also the application for monitoring. So you have to create a 541 mix, but you don't have a 541 loudspeaker system. So this is an application where you can use and where a real measured loudspeaker system is very, very helpful. Just working with your regular headphone, monitor your 5.1 or larger Dolby Atmos on a virtual loudspeaker system. If you are ready, you can export it discretely, so not binaural, but discretely. So you have a master Dolby Atmos, master 5.1 or whatever. Just create it with binaural processing, so without any real loudspeaker. This is one main application, and we have, of course, two tools for that. One plugin you can use in your workstation. Just plug it into your master 5.1 bus or immersive audio bus, and listen to your mix you did in your audio workstation on this binaural loudspeaker system. This is the in-one, the Spatial Audio Designer in-one. And this the Spatial sound card is a standalone application, runs on your computer as a standard audio device. So if you playback anything on your computer, also the output of your audio workstation, you'll listen to it on a virtual loudspeaker system, just with your regular headphone connected to your computer. Pretty easy, and it's a cool application. If you're not so focused on audio workstation production, but also have multi-channel files on your computer, or want to monitor just stereo sound, but you don't have a good stereo loudspeaker system. So there's also an application for binaural audio. But coming back to the main part here for this presentation, how to create binaural audio mixes. And here, the Spatial Audio Designer, it's the first tool of its kind we developed in 2011. Was used from Skywalker Sound to create the mix for Red Tails. It was the first 3D audio movie in Auro 3D in 2012, and it was used to mix this because nobody has something. Such a tool before, also no hardware or something like that. And it is a content creation tool. You can also do monitoring with that, but it is mainly it is a content creation tool, and works in the audio workstation, supports all the formats, and also works in the stereo workstation. So if you just have a workstation with a stereo, and but you want to create 5.1 or 7.1 or Dolby Atmos or MPEG-H, you can use it, but do it with this plugin. And the new version also has an encode for MPEG-H, and has a complete workflow to create MPEG-H and to monitor and to author and to export and to encode. Ooh. And it is object based. I will not go deeper into this here because I think how's the time? Am I good with the time? Okay. Let me just jump into I don't know. This is funny, isn't it? Let me give you a short introduction how this tool works. It consists of three plugins. You use one plugin, the send module, to deliver all the objects in your audio workstation to a mixing engine. We call this a virtual bus. It's running parallel or in the background of your audio workstations, so in your DAW, but your audio workstation do not know anything about that. So you send all your objects to this mixing engine. You have a mix module. It's also a plugin where you can monitor all your sources in and mix them, of course. It delivers the binaural audio of the format you choose to work in. And finally, you also have a channel out modules, but delivers the discrete tracks. You remember creating binaural 541, but export a 541 master without a binaural. This is possible with these channel out modules. So I think maybe have 1 or 2 minutes, further minutes, shall we? Or
yes, you do. No, you've got
good. Then
at least 2 minutes.
At least 2 minutes. Okay, I try to just open here a short Pro Tools session, and I see somebody is also typing something in the chat, but we'll talk about them. This is just giving you an idea for those of you who know what is the work in an audio workstation. It's Pro Tools, very well known, and let me just put this here. And here you can see, here are the send modules. Here are the sources of my mix. Here are the send modules delivering the audio to this virtual mixing engine, the send modules. Here is the mix module. Here you see all your sources. It is always placed in a stereo strip, delivers the binaural audio. And here, additionally, you have the channel out modules. You can see here are the discrete tracks delivered to a real loudspeaker system if you have, or just to bounce it or create a master. And finally, to give you an idea how it looks like in production, like, don't save please. Now I open the Kraftwerk 3D session where I did all the binaural masters in. So it is based on the Dolby Atmos mixes we did. And here I go a step further. I not only use one binaural processing for creating a binaural mix, I use 3 at the same time. So I send all the sources here into these different mixing engines, and I use here 3 mix modules where the virtual buses comes in. 3 virtual buses are running in the background at the same time. And in the first one, I just have 7.1 using the Luna Studio 4. This is what you see here. And the second one, I'm in the binaural, all is binaural here. In the Post Republic, it's a dub stage in Berlin, it's 42.1. And finally, well, I use just a small room, 501. It's a small studio, but I know that the low end is pretty cool there. So I just use the LFE in their rooms, and I just all of these three binaural mixes I send to one bus, sum them in this bus here, do a little bit post processing, and have a master, 2-channel master, what is binaural, where you have a pretty close bed from the Kraftwerk mix, objects running around you in a more distance experience, and the low end, which is just adding a little bit warm air to the mix. So this is very briefly how to create binaural audio. It's our method. It's the way we recommend hands-on. I did it, And finally, here is two links. We can also post them. I can post them in the chat if Polly is doing his presentation, where you can listen to binaural audio just with your regular headphones on your computer. This is a track where the binaural processing I did for the Kraftwerk production. And because there are different ones in the internet where the binaural processing award from Dolby Atmos, from Dolby is used, it's totally different. You will see. And here is our YouTube channel where you can listen to a lot of examples. So that's it from my side. I hope I was not too long. And yeah, for questions, Shelley, do we have now the Q&A or time for questions, or did I?
We have time for a Q&A now. If anybody has any questions, you can write them in the Q&A chat. Otherwise, we can also take them at the end if people need some time.
Yes.
Thank you very much for your presentation.
Thank you.
I have a question. I was quite shocked to your combining the rendering from 3 different studios in one mix.
I did it. And that was pretty cool.
I suppose it's just like using 3 different reverbs. No,
it is. Oh, don't bring binaural, mix up binaural with reverb. It's not a reverb.
No. Okay. I know it's different, but I mean, some people would consider it wrong to use multiple reverbs. It wouldn't have like a natural sound, but that's okay.
Absolutely.
That's the whole.
Check the demos, and you will see. Oh, well, the cool stuff is if you use different binaural processing, the depth of the experience is much better because you create relation. You have something what is pretty close. You have something what is more far away. And because of you hear this what is close, you hear the distance to the stuff what is more far away. And that helps a lot to create space, and also works a little bit more on these effect. Everybody knows with binaural audio that the front localization is always most like that. It's very seldom you hear it like that. But you can increase or improve this experience using such strategies.
I see. Okay, I look forward to listening.
Yeah, good.
To your demos. We have a question from Carl.
Yeah.
Please, can you share Tom's contact details? Yes. There you go. There's some work for you to do, Tom. Yes, we can do that. Do you have any questions, Pauli or Hennes? Oh, sorry. We just got a couple here in the Q&A.
The Q&A. Okay.
Good. So anonymous person has asked, for the YouTube demos where you listen on your own, how does it still work? i.e. without knowing your individual Hrtf and headphones.
The individual Hrtf discussion. Well, honestly, I not really believe in that. I heard my individual Hrtfs, and the problem is 3 measurement, 3 results. It is very complicated to create, let's say, a reliable measurement of your own Hrtfs, and then to use them, and then also to have them with head tracking. So there's just one device in the market, most of you know. But honestly, well, the goal is having the right Hrtfs. This is something what was also touched by Karl-Heinz Brandenburg on the last Tone Master Tagen, as well as from Nico Rosen, a French scientist, and she mentioned this in the Heiser lecture on the IES in Paris. It is well, they did 200 measurements, and finally the users only use 7, more or less everybody. So it is with a good general generic Hrtf, you can finally catch more than 75% people. So this is, so I not believe in you have to have your own Hrtf. It can help, but it is not, my personal opinion, it's not the main goal. So now a long answer for a short question. And what is the difference for Hrtf recording versus measured? Measured from, also I should read it aloud. What is the difference for Hrtfs between recording versus measured? Measured is for measured transfer function, and what is recorded? Recorded is a dummy head recording. Measured is with, for example, with a dummy head, virtual loudspeaker positions, but this also works with an artificial approach, so just doing it with math, and I mentioned the benefit of them before.
That it is more flexible.
Absolutely, it is.
Excellent.
I had one brief question, if I may.
Yeah, please.
I was curious about what did you get any public feedback for the Kraftwerk demo or the Kraftwerk recording? I was curious what people listening to it thought about it.
Oh, we got a Grammy nomination, as you know.
As you know, sorry, I forgot to mention it in the introduction.
Don't worry. And that, and you hear, well, yes, we got a lot of response, and recently I got a response from a well-known colleague in the immersive audience industry, and I don't know somebody who don't like it. So maybe this answers your question. So we got a pretty good response, and we did a test with 40 or 50 people, present them binaural audio. Our method is comparing with stereo and different reproductions, and we also just asked one simple question, one of more questions, but one simple question was, do you like it or not? And more than 85% said, I like it. And this was binaural and this was not binaural. So they could also distinguish this. And this was no professional audio guys. And this is where I say, that's enough. So enough, if we can grab more than 75% of the people well, just like that, and give them also some parameters to do individualization. Also compensation of the headphones. We're also offering compensation for the headphones. You finally grab 90%. And I would say this is, so I don't need personalized Hrtfs if it works like that. Does that answer your question?
Yes, thank you.
Do you see problem in people listening in binaural mixes with speakers? Good question, because actually somebody else point out this problem with listening binaural on real loudspeakers. Well, my personal experience, don't use it on a huge loudspeaker system. On laptop loudspeakers, it works pretty well because you sit so close. You sit in the middle, and it becomes to be, depending on the quality, remember quality of the binaural audio processing, it becomes to be let's say an enhancement of these reproduction applications. So yes, it works, but not always.
Thank you very much.
Welcome.
I think that's all the questions we have time for at the moment. But thank you. It was great to hear you speak, as always. I always like your down to earth. Do the people like it? Yes, they do. It's working. Yeah. Thanks a lot, Tom. So now we will move on to Pauli. Pauli is the CEO of Edon Audio, and that's a local startup here in Copenhagen. He has a background with hearing aids and has been working with spatial audio for how long, Pauli? 25 years?
A bit more than 25 years, yeah.
Yeah, and he has finally started his own company, so he will speak to us a little bit about their audio processing software for VR and AR. Is that what you call it? AR and VR for headphones.
Yeah.
Yeah, so thanks for being here, Pauli.
Thanks a lot, Shelley. And thanks, Tom. Really amazing tools that you have created there.
Yeah, thank you very much.
Okay, so yeah, today I'd like to talk about enabling dynamic spatial audio in wireless headphones. So, you know, spatial audio is not new. In fact, already in 1863, Hermann von Helmholtz said, if the motions of the particles of air in the oral passage are the same on two different occasions, the ear will receive the same sensation, whatever be the origin of those motions. So what that means is that if we can record sound in the ear canals and reproduce it exactly again through headphones, you should be able to hear the same as you would have in the original situation. So that's of course called the binaural recording, but we can use that same principle to create sounds that never existed in the real world, and that is binaural synthesis. And so in the 1930s, Alan Blumlein described how to make a stereo recording. And when you play that back through two loudspeakers in front of you, you hear a sound stage with phantom images between the loudspeakers. Manfred Schroeder described how to do artificial reverberation by electronic means in the 60s. And in the 90s, you know, there was a big interest in virtual reality, and both from the visual side, but also from the audio side. And so in the 2010s, the visual virtual reality and augmented reality really had a big breakthrough, especially with Oculus Rift and the HTC Vive, Google Glass, Magic Leap 1, Microsoft HoloLens. But VR and AR glasses are still not common in everyday life. On the other hand, in audio, there's been a big cultural change where headphones are now everywhere in public. And at least 7 out of 10 people commuting are using headphones. So we see a great opportunity for bringing spatial audio through headphones. Also, our way of consuming media has changed, and communication. So there are many more podcasts these days and audiobooks, and also gaming and online gaming has exploded, and music and movies are bigger than ever before. And since Corona, we've all been sitting in online meetings and seeing the metaverse evolve. And then yet another tendency is that we are starting to put away our smartphones because we realize that they can be too distracting, and also that there are limitations. It's only a visual interface. So instead, when we are wearing headphones, we can interact through the headphones by means of voice interfaces. And this is where spatial audio also comes into the picture, where it can give us an auditory display and really portray the sounds that we are hearing all around us. So the number of headphones are growing exponentially, especially wireless and true wireless headphones. And also edge computing is on the rise. And this is also happening in headphones, where the headphones are getting more and more processing power and memory. And they are getting a multitude of different sensors, similar to what happened to smartphones, actually. And then the headphones are connecting to more and more different devices. And they are connecting also not only through the smartphone, but can also connect through Wi-Fi or 5G or LE audio. Now, the problem is that, you know, we as humans have amazing hearing abilities. And in everyday life, we can hear where sounds are coming from, we can hear how far away things are, and what kind of space we're in. But when we use headphones, the sound appears to be inside our heads. And this is a very unnatural experience that we have come to somehow accept. And that's why at iDune Audio, we have developed some spatial audio software that runs inside wireless headphones to create sounds all around the listener. And then we use motion sensors for fast head tracking. And this is in essence what enables the listener to use their natural hearing abilities. So as I mentioned, the number of headphones are growing really fast. And so if we look at the top of the green bars here, this is all headphones being sold. So to be able to do dynamic spatial audio, we need headphones that are active. And so we can see that the percentage of the total number of headphones that are active versus passive headphones, meaning no processing power inside, is vastly increasing. And then they're all getting motion sensors. So motion sensors are like the inertial measurement units that are in practically every smartphone today. And this is what makes it possible to provide spatial audio to these headphones. So what can we do with such an implementation? One of the applications, as I said, is for interfacing a computer or just the media that we are surrounded by. It can be either with a visual interface, or it could be audio only. So imagine wearing headphones and hearing your email come in and having a volume control down here and hearing battery low signals from behind. Also, when you're listening to music, it's much more compelling to hear it in front of you as a beautiful soundstage instead of all inside of your head. Furthermore, if you're playing a computer game, many games have a 7.1 surround output, and this can be placed in virtual sources around the listener. It's something that's already been done, but being able to make small movements disambiguates the front from the back and makes it much easier to hear where sounds are coming from. When we are watching a movie on an iPad or something like that, or a tablet, even though the picture may be small, the sound can be big and can be like in a cinema. When we're on an online conference, it's very well known that it's much easier to understand what people are saying when they are talking from different directions, as opposed to everybody speaking in your head at the same time. Another application is more like an augmented reality application, where if you imagine a map like Google Maps with a layer of audio sources, and as you move through the city, you can actually hear and interact with these different sounds. It can also be used for navigation, of course, or for information from different stores or whatever. And there are many different applications. Another one could be for dispatchers, emergency services, or fleet control. So with a person who is organizing a fleet of cars can hear where they are in the city around her. Or at work, we can use indoor tracking systems or outdoor GPS systems to actually create beacons where people can navigate to instead of having to watch on a screen. And then finally, also, in some situations, you're forced to wear headphones when it's a noisy environment, and then it's much more natural to hear the sound from the direction of where somebody is speaking instead of having the sound again in your head. So current implementations focus a lot on academic research that have been done during the last 30 years. And here the problems with binaural spatial audio are very well documented. There are things like inaccurate localization, especially cone of confusion errors, so meaning that sounds on a cone to the side here are confused with each other. And the worst type is of course front-back confusion, so sounds that are supposed to be in front here are actually heard behind the listener, or the sounds are too close to the head, or the source sounds too large. And the answer often seems to be that we need individual solutions, just like Tom was describing, these individual Hrtfs. But the problem is that this conclusion is based on static listening in anechoic environments. So this is not how we listen in real life. In real life, we have reflections from the environment. So these head-related transfer functions that describe how sound comes from a point in space to each of the two ears are really essential, but they only describe the direct sound. And we need the reflections very well detailed and also a very good rate reverberation. So one of the key things also is that this issue of listening dynamically versus statically. So we use head movements to localize sounds. So as animals, we have a feedback mechanism that helps us to localize sound and to is an auditory cue. So and that means that if a sound comes from a certain direction and you make a small change, that updates the sound at your ear and helps you to understand where it comes from. And these dynamic cues are much more powerful than static cues, and can create much more accurate and convincing spatial audio. So most commercial solutions have no head tracking, and therefore we see these cone of confusion errors. They are dominant, and specifically sounds in front are often behind, and the sounds are blurry and they are too close. Another thing is that implementations use too much processing power for mobile applications. So they traditionally require a powerful computer, and therefore we need a wired headphone to get low latency tracking. And so the user is essentially stuck behind the computer. But now it's possible to run implementations on a smartphone, as most of you have probably seen. And so in this case, the smartphone is connected to wireless headphones. The problem here is that there's too large delay between moving your head and hearing the sound update at your ear. And that is actually because of the Bluetooth latency that is too large. So Bluetooth has a latency between about 50 to 200 milliseconds. But to have sources that are perfectly stable in space, we need a total system latency below 30 milliseconds. And so the result is that the sounds are sluggish and confusing and gives poor sound imaging. So some solutions actually do run inside the headphone, but then the implementations are rather rudimentary, and most often they still don't have head tracking. So just as a kind of an overview, they either run on a computer, in which case they use too much processing power, or they run in a smartphone, but then there's too high Bluetooth latency, or they're running in the headphone, but then typically there's poor spatial audio quality. So I kind of show it here on the diagonal on this graph. But what we really want is both high spatial sound quality and a high power efficiency, in other words, low power. So headphone manufacturers are saying that spatial audio will be a new driving feature in headphones, just like active noise control has been, or recently also voice pickup and enhancements. And so manufacturers need software that can provide this high spatial audio sound quality and an efficient implementation to run inside the headphones. And that's why we have focused on developing a dynamic spatial audio software that processes the sound in the headphones as opposed to on a smartphone or a computer, and therefore can use this very fast head tracking, because the processing is essentially at the tracker, and by avoiding the Bluetooth latency. So we have a complete spatial audio engine with a low power implementation. And we spend a lot of time of making it work out of the box so that you don't need tedious setup procedures, for example, for getting individual Hrtfs that you have to measure in an anechoic chamber, or use your smartphone to obtain, or something like that. And this makes it possible because it's processed in the headphone. It's independent of the playback device. So it doesn't matter if you use an iPhone, an Android, PC, a Mac, or a TV, or a console. So to be able to do this, we had to make some breakthroughs in the underlying technology, and which has also led to a patent granted on the core technology. So I want to tell you a little bit about this implementation. Basically, it's a physics-based acoustic modeling, meaning that we simulate the listener in a virtual room and among many potentially moving sound sources. And all aspects can change in real time. And then we use, as I said, low power signal processing. So for modeling the direct sound, the head-related transfer functions are actually calculated in real time based on a parametric model. So we don't store any large database of measurements, but although it's been derived from measurements on a very large number of people. So this gives very precise localization due to the infinite directional resolution, because you can calculate any Hrtf. And there's no interpolation between Hrtf. And this avoids coloration, phasiness, and other artifacts. And as I said, no need to store large databases. There are many simultaneous moving sound sources, and they move smoothly due to a time domain sample by sample processing. And so the Doppler effect is inherently implemented. The room consists of the early reflection part, where we have an accurate mirror image model, where you can change the room dimensions, the wall properties, and it uses the same resources independent of the room size. And the reflections react to the listener movement in the room. The late room reverberation is implemented by a proprietary recursive algorithm, which is creating a spatial reverberation decay. So here we found that it's really important that the decay is not just this like a stereo decay, but it actually respects the dimensions of a listener's head. So as I said, we spend a lot of time to make it work out of the box by having a making the solution neutral with respect to the headphone equalization. Also, again, based on a very large number of headphone measurements. But it can be optimized for a specific headphone model if that's necessary. So it's really designed for embedding into headphones, since it uses low processing power and low memory, and gives exceptional performance in battery-driven headphones. And so we have ported this to different processors used in industry. So, of course, what is extremely important is that to show the solutions to different people. And since Corona, we have not been able to travel that easily. So we have made lots of different kits that we could send. And so they typically have a signal processing unit with head tracking on top, and with Bluetooth, Wi-Fi, and a battery, and can be customized to different needs. And so when we actually implement it, the headphone has to have an inertial measurement unit, a signal processing unit, and then we can do the porting. We've also created an app to interact with the headphone that has a lot of functionality. It both runs on Android and iPhone and on a PC, and it controls the parameters either through BLE or through Wi-Fi, but it's really for development purposes. It's not because we think that end users would need this app. But we can change the parameters like moving the listener and the sources, changing the room size and the characteristics of the room, and also the different kinds of signals. So we see that stereo is really one of the main applications where we think stereo is really here to stay, because it works with mobile gaming, listening to music, watching movies, and we have developed an automatic recentering of the head tracking algorithm. So when you watch something on a screen and you move, that the sound actually follows where you're looking. Also in communication, it's much better to get talkers out of your head. It gives a much more natural, intuitive experience, and it can be used for online meetings, ordinary phone calls, but also in customer service centers. And as I said, due to spatial unmasking, it's much easier to understand what's being said when more people are in the call. Also for multi-channel content has become a big deal. We see a lot of new formats and standards, and this can be used for gaming and movies. As Tom mentioned, MPEG-H, there's also Dolby Atmos, object-based audio and ambisonics, but also Bluetooth LE, and 2.4 gigahertz audio streaming, 5G high bandwidth streaming. So we can create a lot of different setups and support all these different standards by simply creating a lot of virtual sources. Also, just a final application I want to mention is a GPS location tracking. So this is an example where you can have a dropped pin on a map, and then you can hear where sound is as a beacon, and then you can navigate towards it if you want. We also have a PC application that gives us more real estate to work with. But in summary, I'd like to say that the key thing is that dynamic spatial audio is fundamentally changing how audio is reproduced. And fast head tracking is essential for high quality experiences. So wireless headphones are now the new norm, because of increasing processing power, and combined with a very efficient implementation, we can have a complete spatial audio engine inside the headphone. And this actually enables the fast head tracking that we need, and the headphone works across all playback devices. And yeah, that's basically what I want to say. Thanks.
Thank you, Pauli. Very
Thanks.
interesting indeed. We have a few questions here. The first is from Stefania from Aalborg University. Could you elaborate on the parametric model you're using for Hrtfs?
Yes. Yeah. So basically, as I said, it was but by looking at hundreds of head-related transfer function of hundreds of different people, and also very, very detailed measurements made on artificial heads. So for just as an example, during my PhD time at Aalborg University, we measured an artificial head at in 2 degrees resolution, meaning that we had 12,000 directions, and this gives very detailed picture of what actually happens to Hrtfs in azimuth and elevation. And from this, and also doing a lot of listening, it's possible to derive what kind of features are actually important for localization in azimuth and in elevation. And so the idea is that we can then break that down to very, very simple filters. And you could see it as an infinite series of filters that could be truncated after a certain time. And so what we find is that by running these very simple filters in parallel, we can both have precise directions for single sources, but we can actually also immediately support many sound sources also at the same time.
Thank you, Pauli. I don't know if it's just for me, but your video has frozen. Is that for everyone else?
Oh, sorry about that.
Oh, you're back again. Oh, it's not frozen. It's just your profile picture.
Yeah, that's weird. Okay.
You're back.
Cool.
So from Martin, how do you solve the problem of playing back binaural source material if headphones apply binaural filtering? 2 times binaural. If needed, we can unmute Martin's microphone if further explanation.
I guess what Martin is insinuating is that sometimes the output from some content may be binaural, and if the content is already binaural, then of course we cannot or should not binauralize that. So if we take the case of gaming, for example, in some games they actually do the down mixing of you get something like a Windows Sonic or Dolby Atmos or THX output, where the sound has already been collapsed to a binaural output, and in that case, of course, we don't have anything to do. But if what we typically would do in a case of gaming is to actually take the 7.1 mix and then create the virtual sources, and then especially since the head tracking is effective, the sounds are stable around the listener.
Excellent. So from Boris, how do you see this tech dripping down to low energy applications?
Yeah, so I think that the point here is that we are already at low energy application. So and that is actually the thing that I think is exciting. So that we have solutions that can run in battery-driven wireless headphones, and so I think it's just a matter of on the one hand, getting it into the headphones, but then also I think at the same time, headphones are getting more and more processing power. So there's more and more possibilities for us to actually create solutions in headphones. So I think if we look back maybe 10 or 15 years ago, all headphones were passive. And then when they started to be active, it was really mainly to get the Bluetooth working, and there wasn't much space for anything else. But these days, we see people adding additional processors in the headphone that make a lot of functionality possible.
So it's not going to be an issue.
Well, I wouldn't say it's absolutely not an issue. I mean, it's difficult, right? I mean, it's challenging and it, especially if we want to run in truly wireless headphones where the the battery is so tiny, it's still challenging. But I mean, that's what we are working towards.
Thank you. Next on the list from Devansh. Is it possible to give any details on the DSP plus IMU hardware used?
Yeah, well, we use a 6 degrees of freedom tracker for most VR applications. So, or what I would call VR, meaning that the actual rendering is not connected to the real world. That could be something like watching a movie, for example, or listening to music. But when we are outside and doing navigation, then we need 9 degrees of freedom. And so because there we need the absolute orientation of the head, and so for the 6 degrees of freedom we have an accelerometer and a gyroscope, and for the 9 degrees of freedom we also have a magnetometer. So I think I could get a lot more into the DSP, but I don't know if this is the right time for that.
No, but your contact information is on the screen here, so I'm sure people can reach out to you.
Sure.
From Jason, do you personalize the parametric Hrtf model according to anthropometric dimensions?
We can do that, yes. So that is actually one of the advantages of the model, so that we can adjust it. But the thing is that we have spent a lot of time in making it work pretty well out of the box. So kind of try, to get the you could say the middle the median head related transfer function, and I think what is really important to understand about having dynamic spatial audio is that it uses the dynamic cues, and these cues are, as I said, more powerful than the static cues. The dynamic cues are also low frequency cues. It's intraoral time difference based, and where the static cues are more high frequency, intraoral level difference based. And that and so at the low frequencies where we have interactions, humans are not that different. So our intraoral time differences are not that different. And that is one of the key reasons why it works so well and why individualization becomes less important.
Thank you, Pauli. Okay, time for one more question. On the slides, you showed headphones for over-the-ear. Does your application also work for in-ear, like AirPods?
Yes, in principle it does. So I guess that question is about this kind of truly wireless, where you have two separate units. So in principle, the engine is, it just takes audio in, it takes tracking data in, and then processes the signal. So but it's a little bit more complicated than having only one processor for the 2 ears, because in that case we'd have to have a processor in both ears, and we need an inertial measurement unit or in both ears as well. Because I think if you want to send the tracking data across the head, then we get latency again. And so it's not that easy, but it's definitely possible. And we are working with a company where we're doing exactly that implementation.
Excellent. Thanks for the answer. But your chip isn't small enough to, or the kind of prototype you have at the moment isn't small enough to put in a very small.
No, and
Like a
I
hearing
think
aid.
some of the prototypes I showed here, they're kind of big and ugly, but I think the what you should I see that I'm still sharing, so I might as well just go to
You are.
I might as well just show some of these demo kits. I mean, basically, our processing unit is on top here, and we, you know, with the inertial measurement unit inside, and Wi-Fi and Bluetooth, and a big battery here, and some wires and things like that. So, but I think how you should think about it is that in most headphones, this is actually built in most wireless headphones. So these headphones are practically passive headphones, so they treat it as passive headphones, and then we have a separate unit outside, and this is kind of a big unit that you know yeah, is mainly just used for development and demonstration purposes.
Thanks a lot, Pauli. I think that's all we have time for. But if anyone else has a question, you can still type it in the Q&A, and then Pauli can type an answer to you.
Sure.
Yeah, so thanks a lot for being here.
Yeah, thanks a lot. And yeah, and if you're interested, yeah, of course, just get in touch.
Yes, we will share all the contact information and the slides afterwards, so you'll be able to get that. And now we have our last speaker for today, Hannes Scamper from Microsoft. Thank you very much for joining us, Hannes, and for getting up early. I was quite surprised to learn when I spoke to Ivan, who's the head of the research group there, that Microsoft are, of course, we know that you're doing research, but publishing over 3,000 papers a year, which is quite impressive. And all of that is available. So if you haven't been reading into it much, you can find a whole lot of information about Microsoft research. And we're going to hear a little bit about the spatial sound research today from Hannes. So thank you very much.
Thank you, Shelley. Can you hear me okay?
Yes, great.
Excellent. Okay, I'll talk a little bit about the spatial sound work and applications we have at Microsoft, and I'll focus mostly on the Microsoft research. So there's a lot of work that goes on all over Microsoft, but this is kind of, these are the things that most of the things that we had some collaboration with or some input on. So let me see here. Right. So I'll give a brief introduction just to explain what I'll be talking about. And then I'll go into some examples of the kind of work that we've done at Microsoft Research in this space, and follow that up with some applications at Microsoft of spatial sound today. And then I'll give a brief conclusion. Okay, so to start off, I'd like to explain who we are briefly. So we're the Audio and Acoustics Research Group. We're a small group within Microsoft Research. So we don't publish 3,000 papers on our own. So there's a large organization that's that has buildings and locations across the world. But we're all located in Redmond, US, in Washington. And these are the faces of our team. And so my name is Hannes Scamper. I'm the guy here at the top. And I'll be talking about some of the work in spatial sound that came out of this team over the past 2 years, plus some other things that are more related to what Microsoft is doing in general. So very briefly, we've heard this now the third time, but I just wanted to put it here to make sure we're on the same page about what I mean by spatial sound or spatial hearing. So we think of it as something that's within the audible frequency and dynamic range of humans. It's delivered usually to both ears of a listener, and it contains localization cues. And so there are a few that I'd just like to point out here. The one that we've heard a lot about already is the head-related transfer function, which kind of describes the interaural time and level differences and some of the spectral cues that give us a sense of where something is in space. But there's also reverberation, and if we so in the right column here, I'm kind of trying to explain how we make that happen if we want to create something that wasn't there before, as Pauli mentioned. So we can use artificial reverb to kind of add reverberation cues, whereas we can use these Hrtfs to impose these spectral and interaural cues. And then we also have dynamic and multimodal cues, and we can use head tracking to encode those into the sounds. And finally, one part here that I think is actually quite important, but very difficult to quantify and control, and it's this idea of expectation and experience. So to give an example, if I'm hearing a helicopter sound, I might be more prone to perceive that as being above my head, or at least outside of my head, simply because I've never heard a helicopter flying underneath me. And so there are some, that's a very crude example, but there are scenarios where in binaural sound we have to work with or against the fact that humans have certain expectations about what things sound like, where they're located in space, and what's plausible and what isn't. And so if the goal is ultimately to create binaural sound that's convincing and plausible, then these are kind of the cues and the realities that we have to work with to make that happen. And if we talk about spatial sound technology, we think of it in terms of three different categories. So there is devices for capturing spatial sound, for example, microphone arrays, or RGB depth cameras if you want to try and do some scene understanding, or you try to work out some Hrdf personalization or other ways of personalizing the audio experience. On the side here, you can see actually some prototype that we work with here at Microsoft Research. So there's a microphone array that has 64 microphones distributed over a sphere and has two fisheye cameras, so you can kind of capture audio and video in a panoramic way. And then below that, we have a rendering device that we used for a long time before head tracking started to be integrated into headphones. We kind of had our own duct tape version of a head track headphones. And of course, there is also head-mounted speakers like the ones you would find in, I believe Bose has nice sunglasses that have little near-ear speakers, and the Hololens, of course, as well as speaker arrays. And in terms of the software or rendering, so ambisonics is one way. Dolby Atmos was mentioned before, and there is a variety of binaural rendering frameworks. So Pauli mentioned their framework. There is Google Resonance, and we also have our own implementation at Microsoft. Facebook has their own implementation, and so on. So that's kind of the landscape of technology in spatial sound. Let's see here. Okay. So I'm going to cover a broad range of topics here, and I'll just give one or two examples of each to kind of illustrate the kind of work we've been doing in this space for the last, I guess, decade or so. So one thing we did, and this is something that I guess anyone who starts working in this space commercially, they start out by collecting their own data. So we had a few hundred humans come into our lab. You can see a picture here on the right, where we measured their head-related transfer functions, as well as a very high resolution 3D head scan and some other anthropometric measurements. So we took some measurements with just manual tools, where we tried to measure people's head sizes and so width, length, height, things like that, as well as a questionnaire to the goal here was just to span a very wide net, get a lot of data from these subjects that we brought in, so that we could then figure out what kind of connections are there between what people look like, or what physically, I mean, in terms of their dimensions, or what other anthropometric features they have, or their 3D scan, and the correlation between that and the Hrtfs that we measured. And so we did actually do some work on Hrtf personalization, and as we heard in the earlier talks, there is valid debate about how much personalization is necessary to get a satisfactory experience. But I guess my argument here would be that if we want to eke out these final 10, 15, 20% of quality and experience or user base, so if you want to actually include everyone in this experience, then some form of personalization might be helpful. And we've worked on a bunch of approaches ourselves, and the literature is ripe with plenty of approaches. So some of the ones that we've worked on were just direct estimation. So assume you have a nice 3D model of somebody's head, you could just go and try and estimate some of these localization cues directly geometrically by running a physical simulation or some ray tracing or something like that. We've tried a model-based personalization, so you kind of use a simple Hrtf model, and you try to adjust that given, again, an anthropometric measurements or a 3D scan of a particular listener. Or you could try and do something based on anthropometry. So you collect some anthropometric measurements of a subject, so they might even just type them in as they set up some device or some experience, and you try to personalize their Hrtfs based on that. And I just wanted to highlight one example of what that might look like, and also something that I think where Hrtf personalization might still be helpful, even if you don't want to go all out with spectral personalization. That's to adjust the kind of the time delay contour or the phase contour of the binaural rendering. And so the very simply, the idea here is our ears are not the same distance apart. So due to that, our binaural experience is kind of skewed or distorted if we listen to somebody else's ears. And so an extreme example would be if I have a dummy head that is very, very small, and I listen to that, and I myself have a very large head, I might hear that the sound stage is either squashed or expanded, depending on whether my head is bigger or smaller than the recording. And what we try to do here is to say, well, if we had something like a single Kinect depth image, it doesn't have to be the Kinect, but that was the device we used. So assume you have one snapshot of somebody's head. Could you fit some model to that head and then use that fitting process to kind of personalize the Hrtfs? And the idea here for using a single image is that in theory, it's very nice to have a full 3D scan, and there are now actually quite sophisticated mobile phone apps even that can do that by using a phone camera and moving it around your head. But it used to be a very, very tedious process. And even with these modern approaches, it's still going to be very tricky to get an actual high resolution scan of your head. There's going to be holes. You won't get much detail around the pinna, most likely. Single shot scan could be helpful to if we could utilize that might be actually realistic in practice to use on a wide user scale. And so there's a paper related to that where we basically just show that by doing this simple mapping, you can improve especially this left-right perception by personalizing the interoral time differences. Another thing that we worked on is we trained a neural network to perform sound localization, specifically in elevation. And the idea was that we could then study how this network performs that localization to understand what kind of features this network relies on in the Hrtf, and see if we can learn something from that. And here's a result, an image here on the right. So the top two images are left and right Hrtfs, the measured reference, if you will, and the bottom two images are the features that the neural network used to perform localization. And you can see that it's ignoring a lot of the information in the Hrtf, but it kind of figured out that there are some peaks and notches in that Hrtf that are indicative of location in elevation. This could be used as a kind of a guide to develop a parametric model like the one Pauli was mentioning. We did some work on acoustic parameter estimation. The idea here is that the acoustics of a space affect how we perceive sounds. And so if you think of an augmented reality scenario where you operate in the real world and then you add virtual content to that world, ideally you might want to match the real acoustics with the virtual acoustics so that the sounds that you perceive virtually sound like they're recorded in the actual space that you're in the physical environment. And to do that, you should try and or you could try and estimate the acoustics of the environment that you're in, either based on a priori knowledge or using cameras, or the approach we took here is using sounds that are in the space that you might pick up with a microphone and see if you can blindly estimate some of those parameters. And specifically, the things we worked on were estimating the reverberation time, which can be a perceptual cue for the size of a room. The direct to reverberant ratio or clarity, which is a perceptual cue for source distance, and room volume. And just again, to give one example here, here's a blind C50 estimation method that we worked on. C50 kind of, so it's the energy ratio of the first 50 milliseconds of an impulse response to the rest of the impulse response. And it's a measure that predicts how reverberant people perceive a sound to be. So if you have a low C50 value, the sound will be perceived to be very reverberant. Whereas if you have a high C50 value, the sound will be perceived as being more dry or clear. And this is independent of T60. So independent of the reverberation time, this is, I feel like perceptually, this is almost a more important cue than reverberation time. And so what we did is we generated a synthetic data set with known C50, extracted some features, and then trained a model to blindly estimate. And you can see some results here on the right of what that looked like. Now, one area that's a little bit more left field, perhaps, is we've started to look at brain-computer interfaces, and one aspect within that space was looking at spatial attention. So the question here was, can we monitor which sound or which direction a person is paying attention to? And you could imagine a scenario like the classic cocktail party where you have multiple people in a room talking to you. And if you were, for example, wearing a hearing aid, or even just one of those augmented reality devices that have a bunch of microphones, if the device, be it the hearing aid or this augmented reality device, could figure out which of these particular people you're listening to or which direction you're listening to, you could use signal processing to enhance that direction and maybe suppress other directions. So you could, simply speaking, decrease the listening effort to kind of perceive a certain person. And you could imagine doing the same thing with pre-rendered content. So whether it's a video conferencing call where you have multiple participants on a call and they're nicely spatialized, or you're watching a movie or playing a game, if we could figure out what you're paying attention to within that that content, we could kind of try and enhance it. And so the example I wanted to show here is monitoring attention to music stimuli. And the way we did this is we had a EEG headset that looks like this pair of headphones that you can see here. So this is just an off-the-shelf EEG device that has EEG sensors integrated into the headset band that's over the head, as well as around the ears. So there's little sponges that are soaked in a saline solution, and they create conductivity with the skin, and then we can measure EEG signals from those sponges. And in the test, we basically to train a model to try and perform this spatial attention monitoring. So in the test, we asked users to pay attention to a particular direction or instrument. I'll play some examples later. And so after we show them the visual cue of what they're supposed to pay attention to, we played a sample followed by a repetition of the same sample. And the task of the user was to determine whether or not the sample changed in the second repetition. The only purpose of this was to force people to really pay attention to what the direction that we're asking them to pay attention to during the test. So this was just there to force people to basically be good sports about the listening test. And then they get a feedback at the end to say whether or not they gave the correct answer. So did they spot whether there was a difference or no difference? And we did this for a bunch of subjects for a bunch of times to collect a bunch of data. And then I was going to show, let's see if this works, just to give you an idea of what this sounded like. So basically we had 3 different instruments that were playing together from 3 different orientations. So let me briefly play this here. So here's an example. We had a vibraphone and we had a piano. And finally a harmonica. The mixture that people were listening to and trying to figure out whether one of those instruments changed in the second repetition sounded something like this. And so the task of the user was in this case to figure out, did the piano, for example, change in the second repetition? And very briefly, the results. If you've ever worked with EEG signals, you'll know that they are extremely noisy and it's very difficult to get robust performance. So here are results for classifying whether or not the person was paying attention to a particular stream. So chance performance here is the dashed line around 60-something%. And we got on average about 70% after doing some signal processing tricks to improve performance. So this is just an example of what you can do with kind of a EEG device that looks somewhat user-friendly because it's integrated into headphones, and then a task that is not terribly far, hopefully, from a practical application. Okay, very briefly, because I see I'm running out of time, very briefly about some of the spatial audio things that are going on at Microsoft today. We have a HoloLens development kit. So this is the HoloLens device that has the spatial sound engine that we've been working on for a long time. Now also in its second version, HoloLens 2. There's full spatial audio support in Windows 10. So it's an object-based spatial audio engine. There's an API for it that you can look up online. So you can create apps that kind of use this spatial audio engine that, again, we've worked on for a long time. Windows Sonic, I guess, is the trade name or the used in the publicly for this the wrapper around the spatial audio engine, and it also provides virtual sound surround sound support. So if you're running Windows 10 and you right click on your loudspeaker symbol, you'll see a little Windows spatial sound option that's kind of using this spatial rendering engine that was initially developed for HoloLens but then found its way into Windows. And there's a bunch of AR and VR headsets available that use Windows Sonic or the Windows Mixed Reality platform. One project I wanted to draw your attention to very briefly, this is not from our group, but it's from another group within Microsoft Research, is Project Acoustics, which is acoustic modeling for interactive applications. So you provide this thing a 3D mesh of your scene, and it will generate an acoustic simulation, and then a binaural interactive rendering of it. So it's a plugin for Unity and Unreal that kind of does this acoustic wave-based simulation of acoustics. And two projects I wanted to very briefly highlight. One is Cities Unlocked, which is a joint project between Guide Dogs UK, Microsoft UK, and MSL Labs in Cambridge and Redmond. They had a custom headset device with IMU and smartphones, and the idea was to unlock a city or cities for visually impaired people. So imagine walking through a city. The app and the device would kind of unlock the city for you by verbalizing information around you or giving cues and navigation and things like that. And in the same sphere, Soundscape is an app that was developed at Microsoft Research, which provides kind of ambient awareness, not just to visually impaired. It's intended for everyone. And it uses binaural sound and kind of the engine that we've been working on for a long time here at Microsoft Research to provide this ambient awareness of your environment. Okay, that brings me to the conclusions. So I'd argue that spatial sound research and technologies are regaining momentum. So they've been there for a very long time, as Pauli mentioned earlier. But with this resurgence of mixed reality, and also now we start seeing it in productivity scenarios, people are again very interested in spatial sound. So there are some old research questions that people still work on that aren't really solved, like how do you assess the quality of spatial sound? How do you create nice externalization, especially if you have to do it with very limited resources in terms of compute and battery? Is personalization relevant or not? I'd argue that for certain aspects, like I mentioned, just the general dimensions of the head, it can be interesting if you want very high precision for localization, but there are other aspects to it. And then there are some new research questions that kind of emerged with new applications. So we have, with remote work and mixed reality, we have some new use cases for spatial sound that we kind of need to figure out how spatial sound can be used very efficiently in those. We have questions about multimodality. What happens if you combine video and spatial sound? What happens if you add BIOS signals like the EEG sensors I mentioned, or other sensors that kind of give us information about the user? Or how do you compress spatial sound? Things like that. And with that, I thank you very much for your attention, and I'm open for questions.
Thank you, Hannes. Very interesting, and you managed to cover a lot in in that time. Let's see here in the questions. We have a question. Could you say a bit more about which feature of the EEE signal you use to estimate the attention? What is the input to the AI?
Yeah, so the idea was to use an envelope follower in audio and in the EEG signal. So it's time domain energy envelope, and we were trying to find a good correlation between the envelope of the EEG signal and the energy envelope of the audio, the three audio streams. And the details are in the paper, but basically the model tries to figure out how to mix the different EEG channels together to produce an envelope that would then be correlatable with one of the audio streams, and then figure out which of those streams was the one that the user was actually paying attention to. So the idea here is that if you're paying attention to a particular envelope, your EEG signals, or a mixture of those signals, will actually exhibit some of the same temporal structure, or it will be enhanced compared to the streams you're not paying attention to.
Excellent, thank you. I was wondering if you could say a few words about the HoloLens. I know you worked on the audio integration for that, both the hardware and the software. Yeah,
so the HoloLens was it was an interesting project because it was we worked in extreme secrecy for a long time on it, and basically because it was a brand new device, almost you could say a device category, we had to develop a bunch of algorithms from scratch. So both on the spatial rendering side, but also capture of audio, speech enhancement, and things like that. And very close collaboration. So Microsoft Research is kind of the research arm of Microsoft, and sometimes they can be a little bit separate. So Microsoft Research does their own projects and has their own funding and all that. But in this case, with the HoloLens, we worked together very, very tightly, had very, very close integration with the product team to kind of get spatial sound and other sound algorithms running on this this device that is completely battery driven. So there were a lot of the constraints that Pauli mentioned in his talk were also true for the HoloLens.
But were there was it binaural in the end?
Oh,
or
yes,
did you have
yes.
other
Yeah, so it was a fully blown, or it is, I guess, a fully blown spatial rendering engine, object-based, that uses Hrtfs and artificial reverb and integrates head tracking from the HoloLens, and that same or a version of that engine then found its way into Windows 10. So that's what I'm saying now. In Windows 10, there's actually full spatial sound support. It's a bit hidden in the APIs, but if you just want to try it, the Windows Sonic for headphones option in your spatial sound settings kind of gives you an idea for certain content what that might sound like.
Great, thanks. We have another question here from Satish. Would you please explain a bit more about how the binaural thing is implemented in wave-based acoustics projects?
Yeah, so the project Acoustics does the acoustic simulation. So it's a very nice way of analyzing the space physically offline, and then you have a way of running it in real time. The output of that simulation basically goes into that same spatial rendering engine that we use or a version of it that we use in the HoloLens and that we use in Windows 10. So there's a Unity plugin for Hrtf rendering or binaural rendering that uses our engine, and the project Acoustics internally plugs into that plugin and gives you a binaural experience if you wish for a virtual reality headset or headphones. So that system is actually used for some games, which I can't name off the top of my head because I wasn't involved in that. But there are some games, some Xbox games that use this engine, this Project Acoustics engine to drive the acoustics and drive the audio experience. I hope that answers the question.
I hope so too. Pauli has one question.
Hannes, if I understand correctly, you used an AI to analyze the cues, and especially elevation cues. Could you say something about what did you find out? So what cues are important for elevation, and can they be related to certain features on the body?
Right. Yeah. So this was an intern project, and the intern worked on this for 3 months, and we were very happy to see the initial results. To be very honest, we could have put more time into digging deeper. So the main takeaways that we found based on the experiments that we did within the scope of this internship was that we tried very hard to make sure we forced the network to kind of perform localization the way a human would do. So we just give the network a brief binaural sample and had to figure out elevation from that. And when we then look back at the features, we saw some of those frequency dependent notches and peaks that kind of shift in frequency as a function of elevation, plus some high frequency stuff that we thought was maybe less relevant for humans, but that the network seemed to be picking up. But we didn't look at, which is actually a great idea for a follow-up study. We didn't look at, can we relate those features? Can we somehow extract from this map a correlation between those features and some anthropometric data that we have for the subjects? So we used some public Hrtf data sets to create the samples. And I think the CIPIC data set, for example, would have some anthropometric data. So we could have, that's a good idea. We could have looked at at whether there's a correlation there.
Okay, thanks.
So if there's any students out there looking for an internship at Microsoft,
Right. Yes.
they have
Every
a very
summer.
good intern program right here. Internship program, yeah. Great. Unfortunately, I think that's, yeah, we've gone a little bit over time, so I think we have to wrap it up for today. But thank you very much, Hannes, and thank you very much, Tom and Pauli, for being here. 3 very interesting presentations, and like I said, we will share those afterwards. And thanks to our audience for attending. There was quite a big crowd today, and I think a lot of hearing aid and headphone manufacturers involved, so that was great. Oh, Soundbeck has one question. Soundbeck, do you need to write it? No, right, okay, that's it. You put us on down, good. But thank you very much. And if everyone, if our attendees could spend 1 minute filling out the questionnaire, that would be very helpful. We put on these events and they're going to be free. A lot of thank yous coming in here in the chat. Yeah, they're going to be free and there'll be a lot of them. So if you have any feedback or suggestions and ideas, we would love to hear from you. And yeah, thanks very much, everyone. See you next time.
Thank you.
Thank you,
Thanks,
too.
Thank you, everyone.
Bye.
Bye. Bye.
Bye.